NASA spent $93 billion on the Artemis moon program. The rocket designed to carry astronauts back to the moon has flown once, but without a crew. Now the next mission has missed its launch window because of a helium-related issue in the same upper stage pressurization system that NASA also reviewed against Artemis I data. One rocket, one uncrewed mission, one repeated failure mode. And before a single astronaut has left Earth orbit under Artemis, the program itself has already changed course. What's really wrong with NASA's Artemis moon plan? Here's what actually happened. Artemis II had been targeting launch opportunities as early as February 2026. The mission was supposed to mark the first time that humans would fly beyond low Earth orbit since the Apollo era. But during final launch preparations, engineers identified a helium flow interruption inside the interim cryogenic propulsion stage, or ICPS. This stage sits on top of the Space Launch System, the rocket that lifts Orion spacecraft into orbit. Once the rocket reaches space, the ICPS performs the burn that sends Orion toward the moon. The problem appeared during a routine pressurization sequence. Helium is used inside rocket stages to push propellant through the fuel system and maintain tank pressure. Without a stable helium flow, the propellant system cannot operate reliably. A similar flow interruption had occurred during Artemis I in 2022. Same subsystem, similar pattern. During Artemis I, the issue did not stop the mission because that flight carried no astronauts. But Artemis II is a crewed mission, and the standard for risk changes when humans are on board. NASA therefore made the decision to roll the rocket back to the vehicle assembly building for additional investigation and repair. That rollback alone pushes the launch to no earlier than spring 2026. The ICPS itself is not a completely new design. It is derived from the Delta IV upper stage, originally built by United Launch Alliance. The stage performed successfully during 2 full wet dress rehearsals before launch. But the helium flow interruption appeared during routine repressurization. NASA treats it as a system behavior requiring investigation. So the Artemis schedule paused, and then 2 weeks later, the architecture of the program itself changed. On February 27th, NASA Administrator Jarek Isaacman announced a major restructuring of the Artemis mission sequence. Artemis III will no longer attempt the first lunar landing. Instead, Artemis III will become a low Earth orbit systems test scheduled for 2027. The exploration upper stage, which was originally designed to increase the capability of the SLS rocket, has been canceled, and the first crewed lunar landing has moved further down the mission chain, now assigned to Artemis IV in 2028. The mission sequence now has been redesigned before astronauts have even flown the second mission. The question is whether the Artemis architecture itself creates pressures that are difficult to solve. And to understand that, you have to understand a single orbital mechanic constraint that shapes everything downstream. The biggest constraint in the Artemis architecture is surprisingly simple. Orion does not have enough propellant margin to safely operate in low lunar orbit and still guarantee a return to Earth. Instead, the spacecraft remains in a distant orbit called a Near-Rectilinear Halo Orbit, or NRHO. This orbit sits thousands of kilometers farther from the moon than the orbit used during the Apollo missions. During Apollo, the command module stayed in low lunar orbit, while the lunar module traveled a relatively short distance down to the surface. Under the Artemis architecture, the Human Landing System, or HLS, must travel a significantly longer path between NRHO and the moon's surface. NASA has selected 2 providers for the Human Landing System, SpaceX's Starship HLS and Blue Origin's Blue Moon Lander. Both must be ready before a crewed landing can proceed. Now, that single constraint cascades throughout the entire system. A longer travel distance means more fuel, which means more launches. Those launches will carry tanker versions of Starship that refill the lunar lander in orbit. More tanker flights mean more orbital refueling becomes a critical step in the mission chain, and orbital refueling at this scale has never been demonstrated operationally. So, a single architectural decision multiplies complexity across the system. At the same time, the Space Launch System is still encountering recurring technical issues, such as the helium flow interruption as seen on Artemis II. The system works, but it is also expensive and difficult to operate frequently. Now consider the budget layer. Between 2012 and 2025, the Artemis program accumulated approximately $93 billion in total spending, according to a NASA Inspector General audit. Each launch of the Space Launch System costs roughly $4 billion. That cost level puts pressure on NASA's exploration budget because SLS and Orion consume a large share of the funding available for the lunar program. In the fiscal year 2026 federal budget proposal, the White House suggested ending the SLS and Orion programs after Artemis II. That would have saved roughly $879 million per year. Now, Congress overrode that proposal, meaning that the program continues. But the debate revealed that the long-term affordability of SLS is an open question even inside the government. On February 27th, the Artemis architecture changed in 3 significant ways. First, the exploration upper stage was canceled. Second, Artemis III became a low Earth orbit systems test instead of a first lunar landing. Third, the first crewed lunar landing moved to Artemis IV in 2028. Future SLS launches will now use a modified configuration with a replacement upper stage that has not yet been publicly confirmed. If that is not ready in time, Artemis IV could slip again. The lunar landing also depends on an entirely different system, Starship. Before astronauts land on the moon, Starship must demonstrate 3 critical capabilities. First, orbital refueling must work reliably. Second, the Human Landing System variant must pass NASA certification. And third, the spacecraft must demonstrate that its heat shield can survive Earth re-entry from lunar return speeds. None of those steps have been completed yet. The February 2026 restructuring reduced direct dependency on Starship certification timeline by moving the first crewed landing to Artemis IV. However, if both Starship and Blue Origin's moonlander miss their 2028 window, a crewed lunar landing won't be possible on schedule. To understand why the Artemis architecture looks this way, it helps to compare it with earlier programs. The Apollo program followed a very deliberate demonstration sequence. The Saturn V rocket flew twice without a crew. Apollo 7 tested the command module in low Earth orbit. Apollo 9 tested the lunar module in Earth orbit before any attempt was made to land on the moon. Artemis follows a different path. The Space Launch System has flown once without astronauts. Artemis II will carry astronauts on the second flight. Artemis III is now a low Earth orbit systems test, and the first lunar landing will occur during Artemis IV. The same pattern appears when you compare how different programs approach crew certification. Before certifying Falcon 9 for astronaut missions, NASA required the vehicle to complete 7 flights without major design changes as part of its certification standard. For SLS, the certification threshold is effectively 1 uncrewed mission. This difference is not about the engineers who designed the rockets. The engineers involved in both systems are extremely capable. The difference lies in the institutional framework surrounding each program. Apollo operated under a Cold War national priority with a single clear objective. Commercial crew programs use fixed-price contracts and repeated launches that gradually build reliability. Artemis operates under a political framework that requires NASA to reuse shuttle-era hardware and workforce infrastructure across multiple states. Those decisions help preserve jobs and industrial capability, but they also shaped engineering architecture. The Space Launch System exists partly because Congress required the shuttle-era facilities and expertise in states like Alabama, Texas, Louisiana, and Florida to remain active. The result is a system that must satisfy engineering requirements, institutional commitments, and political mandates simultaneously. And that is why the Artemis architecture looks more complex than Apollo's. NASA has now spent $93 billion on Artemis, flown once without a crew, rolled a rocket back to investigate a recurring helium issue, canceled the exploration upper stage, and redesigned the mission sequence before astronauts had even flown beyond Earth orbit. SpaceX is building the lunar lander for $2.9 billion, roughly 3% of the program's total cost. The first lunar landing has moved to Artemis IV in 2028, and the architecture now depends on technologies that still need to prove themselves in space. If Starship is not certified in time, what decision does NASA have to make, and what options will remain?